Okay, let's go through this. So looking at the 29 exam, so we've got an interference pattern. Now just to start off with, this is referred to as 0. 1, 2, 3, 4, 5, 6, 7, 8, 9. So there are 9 divisions for distance B. A lot of students will start counting at 1, which is a rookie mistake. If you look on your ruler, you notice that the ruler always starts at 0. So there are 9 divisions there. Okay, we are told the distance between the slits, 1.9 meters away. So that's the length. So we've got all our values. We've got 2 distances there. Automatically there's going to be an exam question saying which one is the better one. You're told 91 millimeters and distance A was 11 millimeters. So question number 1, explain why measuring distance B demonstrates better experimental skills than measuring distance A. Well, if you make an error by 1 millimeter here, is going to be far more larger than if you make a 1 millimeter measurement error there, because then that's going to be divided by 9, so that's going to be less significant effect on it. So just put this in words. So measuring error is reduced, becomes more precise, and I'll just put in an example here. So here, if you did a plus or minus 1 millimeter error when you're doing measurement, if you do it at either end of here, then it'll just become plus or minus 1/9. So significantly decreasing it. Distance B was used in the calculation, which is good because that's the more precise one. So let's have a look. We're told what the distance between the delta Y there, between the bright and dark bands. So we've got 91 divided by 9 bands, which gives you 10.11 reoccurring millimeters. So if I do that to 2 stick figures, that's going to be 10 millimeters. And if I change that to meters, then that becomes 1.0 times 10 to the power minus 2, alright, which matches up with the question there. Determine the wavelength of light used in the experiment. So delta Y is equal to wavelength times by the length from the distance of the screen, distance between the slits if I actually rearrange that. So delta Y is equal to wavelength times by length over distance. So if that's times by, so on the other side it's divide by, or I can actually invert and multiply. So distance between the bands, I didn't really invert it there, did I? Is equal to the wavelength. Substitute my values now, so that's 1.2 times 10 to the power of minus 4 times by 1.0 times 10 to the power minus 2 over 1.9, and that gives us 6.3 times 10 to the power minus 7 meters. Don't forget your units. Explain how the bright fringes and the patterns on page 6 were produced. Notice how it's only talking about bright. Don't write anything about the dark areas. So that is going to be constructive interference. How are we going to get constructive interference? That's when the optical path distance is going to be a whole multiple of the wavelength. Okay, question number 12 here. Diagram shows two rays of monochromatic light going to diffraction grating. Each ray passes through a different slit on the diffraction grating. Alright, let's have a look here. The nth maxima occurs when rays 1 and 2 constructively interfere. This maximum occurs at angle theta. Show that d sine theta equals the multiple of a wavelength, where d is the distance between the slits on the diffraction grating. Alright, so this is d in here. If I then draw a constructive line at right angles to here, d is technically the hypotenuse. The angle theta is in here, similar triangles, and that would be the adjacent side, and this one would be the opposite side, if I was doing some trigonometry. Now, that opposite side is also equal to, that's the optical path length, that's equal to a multiple of a wavelength. Alright, so just change my pen here. Sine of theta is equal to opposite over hypotenuse. Now the opposite side was equal to m times wavelength. I can still see it up here. And the hypotenuse was the distance between. Alright. So adjacent theta d, there's the right angle in there. So we have sine theta is equal to multiple of wavelength over the distance, that's divided by, so on the other side it would be times by, can't do my thetas very well, and that's equal to that, and then it's all good. Alright, so the light has a wavelength 5.89 times 10 to the power minus 7. Diffraction grating contains 300 slits per millimeter. So remember, times that by 1000, and then that will give you your slits per meter. So that will be 3 times 10 to the power of 5. So the distance is going to be the inverse of that. I'll just leave that there for now. The third order maxima, so m is going to be equal to 3. Theta we don't know, and the wavelength we do know, so that's 5.89 times 10 to the power minus 7 meters. So let's go to our equation, our tool to solve this. D sine theta equals m over lambda. Sine theta is equal to multiple of the wavelength over the distance between the slits, and of course if I want theta I'll do the inverse sine of that. Let's substitute my values in. So theta is equal to sine 3 times 5.89 times 10 to the power of minus 7 divided by 3 times 10 to the power 5, so theta ends up being 32 degrees. So monochromatic light, we've got a wavelength here. Remember, nano is equal to 10 to the power of minus 9. Coherent light source between two slits. Okay, so there's your D value, interference pattern is produced, and that's going to be my L value. So let's grab our equation, our tool to do this one. So that is y is equal to the wavelength times the length from the screen divided by the distance. Let's substitute our values here. So delta y is equal to 589 times 10 to the power minus 9 times 0.75 and over 2.4 times 10 to the power of minus 4. So separation between the slits will be 1.8 times 10 to the power of minus 3 meters. Just remember you are looking for a small value, so if you don't get one, go back and fix her up. Students using a spectrometer. Okay, so that's just going to be a very precise way of actually measuring the angle. Diffraction grating, determine the slits on the diffraction grating. So rather than having a delta y value, you're going to have an angle theta. So this particular student, for different orders of maxima, so here you have them, they actually measured theta and then worked out the sine of it. And it's a nice linear relationship, which shows a direct proportionality, which is something that you would expect. The equation of the line is such and such, very low value, so we can actually say that's a low systematic error. However, this slope is the one we're going to be looking at, because when you get a question like this, when they say the slope, then they're actually looking at order of maxima, so that's your m values, and you've got your sine beta, which is your y values. Because remember, slope of a line, or the gradient, is equal to delta y over the delta x. And in this case, it's going to be sine theta over m. So we're going to have to, automatically I already know that I'm going to be rearranging my equation, substituting this value in here for, what have they got there? 0.18. So there's going to be a bit of tricky rearranging. Using the gradient line of best fit, determine the number of slits per meter on the diffraction grating. Surprise, surprise, as he says sarcastically. Alright, so the gradient is equal to change in y over the change in x, which is going to be sine theta over m, which is going to be equal to 0.18. So the equation d sine theta is equal to the order and the wavelength there. So I want to rearrange this equation so it says sine theta over m. So that's times by, on the other side it will be divide by. So sine theta over m is equal to lambda. Now that's times by, so on the other side it will be divided by. And of course remember this is going to be equal to 0.18. So now I can forget about this because I've already worked, or the equation of lines already worked it out for me. The other value that we have, so d is going to be equal to the wavelength divided by 0.18, and the wavelength was 589 times 10 to the power minus 9 over 0.18. So the distance between the slits is going to be 3.26 times 10 to the power minus 6 meters. Now, a lot of students would leave it at there and not get full marks, because the question actually says slits per meter. Alright, so to get the number of slits, we do the inverse, so that's going to be 1 over 3.26 times 10 to the power minus 6. So the number of slits we're going to have is 3.1 times 10 to the power of 5. Slits per meter. I'll just write the lazy way. Alright, let's have a look at this 2017 one. So we've got delta y values here. We're actually told that d is 4 times 10 to the power minus 4 meters apart. We've got L and we've got delta Y, and I can see the hint of a graph, so that means there's going to be a slope or a gradient. So a bit of rearranging, just like with the previous question. Alright, so slope or gradient is going to be equal change in Y over the change in X, and our Y values here are conveniently the separations between the bands and also over length. So that means I'm going to rearrange my equation sort of correctly. So we're going to have this slope value, and if you scroll down here, we're actually told what the slope value is. Alrighty, let's get this started. So the slope equals change in Y over the change in X, which is equal to band separation divided by the length to the screen. Now the equation is delta Y is equal to wavelength, length of distance from the screen, over the separations. Now if I rearrange this, so that can also be expressed as wavelength divided by D times by L. So if that's times by L, on the other side it will be divided by L. So delta Y over L is going to be equal wavelength divided by distance, which is going to be equal to 1.6 times 10 to the power minus 3. Now, we do know the D value here because it was given before. So that's divide by, so on the other side it's going to be times by. So wavelength is equal to 1.6 times 10 to the power minus 3 times by 4 times 10 to the power minus 4, which is going to give me 6.52 times 10 to the power of minus 7 meters. Don't forget the units, otherwise you're going to get ping marks. Alright. Describe one way to improve the precision of this student's data. Okay, so let's go back here. So what we want is to measure those distances more accurately. So rather than just doing it across 2 maxima, we do it across the lot of them and actually divide it as per the previous question. So that's one way of doing it. So what we want to do is measure across more orders or maxima. Alright, now if we look at the graph there, we've actually got L on the x-axis and the change in the band separation is on the y-axis. So what we could do is probably get some more data across for L. So what have we got there? More samples of L. Which is the distance from the slits to the screen. And what we could do is also with the slits, rather than a double slit, we could actually have a multiple slit, because then the transition from bright to dark is going to be more definite, more precise, so you can actually do more precise measurements. Okay, the students then doubled the distance between the slits, one value there. Alright, what's going to happen? So we're going to be looking at a ratio. So more or less what's going to happen if you move the screen back, the band separation distances are going to increase. Okay, so the values between delta Y are going to increase because it's actually directly proportional to the length to the screen. Alright. Alright, so let's have a look at this one here. So we are in this device here, rather than it being projected on a screen, we're actually going to measure the angle. So we're going to be looking at equations that don't use delta Y. We're going to measure that very precisely. We have a light source that goes through, and you can actually measure it the angle because it will be actually on the side there. Diffraction grating is 450 lines per millimeter. You'll need to convert that to meters. We've got theta at 15.4 degrees. And that's going to be the first order maxima, so that means m is going to equal 1. Alright, so let's actually go through this one. So the number of slits is going to be equal to 450 times by 1000, which is going to give you a value of 4.5 times 10 to the power of 5. And the distance will be the inverse of the number of slits you got there. And I'm just going to leave it like this because I'm going to do a sneaky and be slack with the calculator. So the wavelength is equal to d sine theta over m. Okay, and I'm just going to cheat here because that distance is going to be 1 over 4.5 times 10 to the power 5 times by sine of 15.4 divided by the order or maxima, and that was equal to 1. So that gives us a wavelength of 5.9 times 10 to the power of minus 7 meters. Don't forget the units. Alright, the student then replaces the monochromatic light with white light to describe the first order maximum spectrum that's now observed. So for the first order, for the zeroth order, you're going to end up with the white one. However, on the first one, you're going to look at a spectrum of colors. So this is when you're actually looking at the rainbows on the surface of a DVD or CD. Okay, so the high frequency violet's going to have the smallest angle because higher the frequency, the less diffraction occurs. The lower the frequency, the more diffraction occurs. So just to cheat, low frequency reds are going to have the largest angle as they diffract more. And that is the end of the video. Thank you.